This is a quick reminder on how to model rotational motion. So there are no new Newton's laws. It's simply F equals ma applied in a rotational setting. So instead of force is equal to mass times acceleration, the force we talk about are now moments about a center of mass. And so it's the sum of all those external moments, just like it's the sum of forces. And instead of mass, now it's the moment of inertia. And so that is something that depends, as you know from previous classes, that's something that depends on the shape of the object, whether it's, let's say, a long bar or a flat disk or something like that, a sphere. And then finally, the angular momentum, which is the second derivative of the angular position. So just as a simple example, so in this case, we could model a satellite's attitude, so its angle with respect to some particular reference, and we could use variable theta to describe that. And so in this case, theta could represent the angle from this reference such that aligns that way. Moments could happen due to, for example, this gas jet could essentially create a force that pushes the satellite like this, and that would induce a rotation, this clockwise rotation. And so the way that you would identify that moment is simply just that force applied at that distance. And so that's the force multiplied by that distance gives you the moment. And then you could also have some other moments that could be either due to other gas jets or, for example, in this case, some sort of disturbance moment, and that would also add to it. And so this combined would then be your combined moments. You would then use your moment of inertia, and then you would have your second derivative of your position. And so just like the previous examples where we had F equals ma, this gives you a second order differential equation that then models that system.